Section 3.8, Rates of Change in the Sciences. So calculus really is all about measuring change and how fast things change and rates of change. And this is not just some random theoretical thing that we do, it actually has some very important applications. And we're going to look at some of those in this section. And the actual derivatives we take in this section generally are going to be pretty easy. The difficulty lies in figuring out sort of what the question is asking and how to use calculus to get there. So our first example is from physics. And here we have a particle motion. So what's going on here is this is a function representing the position function for a particle moving along a number line. So the idea is you've got a number line here. Here's 0, 1, 2, -1, -2, etc. And at a certain time here, if you plug in 0 for t, it cancels out everything. So your particle is at the position of 0 when t is equal to 0. Then when you plug in larger numbers of t, you might get a positive number or you might get a negative number, so it could be moving to the right or to the left. And we're going to use calculus to figure out some things going on with the particle. So question A says find the velocity at time t. Remember, velocity is the same thing as the derivative of the position function, and this is our position function. So we take that derivative and we get 3t squared minus 18t plus 24. That's my velocity function. B says find the acceleration at time t. Acceleration, well, that's just the derivative of velocity, and the derivative of velocity is the same thing as the second derivative of my original function, which is just the derivative of this function, which is 6t minus 18. Then question C says, when is the particle at rest? That is, not moving. If you're not moving, that means your velocity is 0. Okay? So we want to find the time when the velocity is 0, so we set this equation up here equal to 0. 0 equals 3t squared minus 18t plus 24. Now this looks like a quadratic expression. I could use the quadratic formula to solve it, or I could solve it using factoring. And I'm going to do it that way. I'm going to actually factor a 3 out of this, and I get t squared minus 6t plus 8, and I can factor that as t minus 4, t minus 2. So this will be 0 when t equals 4 and when t equals 2. So I'll say at t equals 4 and t equals 2, the particle is at rest. So in other words, what's going on here is the particle's moving somewhere. After 2 seconds, it's got to a particular spot and it stops. And I don't know if it's moving forward or backward, but it stops and then it goes somewhere else. And then at 4 seconds, it stops again. Question D, what is the total distance traveled by the particle in the first 4 seconds? And I say, note, this may not be equal to f of 4. Well, let's just calculate f of 4 real quick. Remember, my original function is t cubed minus 9t squared plus 24t. If I plug in 4, that will tell me the position of the particle at 4 seconds. So that would be 4 cubed minus 9 times 4 squared plus 24 times 4. And when you put that all into your calculator, this is like 64 minus 9 times 16 is 144. 24 times 4 is 96. This comes out to being 16. It means that my particle is at a position of 16 after 4 seconds. But I want to know how far it's traveled in the first 4 seconds. And I know it started at 0, but I also know that the particle stopped at 2 seconds. So maybe the particle went past 16 and then came back. So let's figure out how far or where the particle is at 2 seconds, and then maybe that'll give us a sense of what's going on. So f of 2, and remember we did 0 before, f of 0 was 0. If I do f of 2, that's 2 cubed minus 9 times 2 squared plus 24 times 2. This gives me 8 minus 36 plus 48. That gives me 20. So what's going on here is the particle started at 0. After 2 seconds, it goes all the way up to a position of 20. Then it stops, and then it moves backward to a position of 16 and stops again. So this implies that my total distance is equal to 20 plus 4, where the 20 is the distance from t equals 0 to t equals 2, and the 4, so the total is 24. This is my distance from t equals 2 to t equals 4. So when you're looking for total distance traveled, you don't just want to look at starting position and ending position. You also have to know where the particle stopped and figure out the distances in between each of those. All of a sudden my scrolling has stopped working. Graph f of t, f prime of t, and f double prime of t on the same set of coordinate axes. So this is the position function, which maybe I'll do in green. The derivative, that's the velocity function, I'll do in blue. And the acceleration function I'll do in red. So my original function, f of t, that was the t cubed minus 24t, or minus 9t squared plus 24t. And if I graph that, let's put some numbers on here. This is 8, 16, 24. Do those for negatives as well. And then let's say this is 4 seconds and this is 8 seconds. So if you graph that original function, it comes up here and right at about 2, remember it got to a position of 20, and then it went backwards and ended up at a position of 16 at 4 seconds, and after that it actually goes back up again. So that's what my original function looks like. That's f of t. F prime of t, that's the 3t squared minus 18t plus 24. That's a parabola. It's a squared function. And we notice that that hits 0 at 2 and 4. That's what we figured out before. And it crosses the y-axis at 24. So I can make this sort of come down, come up here, and then go that way. Again, these are just rough graphs. And then f double prime of t, my acceleration function, that's just a line. And I think it crosses down here at negative 18, and it has a slope of, I think, 6 or something like that. Let me look back at it. Yeah, slope of 6, and y-intercept is negative 18. So that'll end up crossing my x-axis at a 3, and those are the 3 graphs. And notice that the 2 places where the f of t had a horizontal tangent line, those are the places where my derivative crosses the x-axis. And here, where this function has a horizontal tangent line, that's where my red function, the acceleration function, crosses the x-axis. And then the last one is find the position of the particle when its velocity is 45 meters per second. What I'm doing is I'm just going to take 45 and I'm going to set it equal to the velocity function, which is 3t squared minus 18t plus 24. Subtract the 45 over 3t squared minus 18t minus 21. Again, I could use the quadratic formula, or I could factor. This will be 3 times t squared minus 6t minus 7. That factors to be 3 times t plus 1 times t minus 7. And our particle, we're thinking of it moving with positive time, so we actually toss out, we get t equals -1 and t equals 7 as two possibilities. We toss out the negative time value because we're thinking of time starting at 0. So t equals 7, that's the time when the velocity is 45 meters per second, but we want the position. So we now have to take t equals 7 and plug it back into the original function. So that's 7 cubed minus 9 times 7 squared plus 24 times 7. And when I plug all that in, I get a position of 70. So at that point, it's actually on the number line at the position of 70, and it's moving 45 meters per second.